Oh, hi there, everyone. Thanks so much for showing up for your math learning. This is, as advertised, our ultimate lesson today. So we are wrapping up our work on logarithmic equations and graphing the functions. After that, I have a quiz on working with logarithms. Tomorrow we will have another quiz on solving logarithmic equations. And then Thursday is just general logarithmic and exponential review, and Friday is our logs test. Next week and Monday of the week following is just pure exam review, which is great. We get to review all the topics. We can do some Kahoots. We can gamify our learning. You can ask me questions. You can use the AI tutors. You can use the Mr. Jennings tutor. We can level you up for calculus next year or university, okay, for future challenges. So for today, let's dive in. We are looking at transforming logarithmic functions. So we want to be able to transform them, graph them, or even state the equation of a logarithmic function given a set of transformations. So one thing to recall is if you were strong at exponential functions in grade 11, you know, they looked like this. They were asymptotic to the x-axis, and then they hockey stick up and sort of start their huge growth at some point. Okay? If you were to just reflect those graphs in the line y equals x, because logarithmic functions are the inverses of exponential functions, they would look like this. They're asymptotic to the y-axis now instead of the x-axis, and then they hockey stick this way and go very level. They really flatten out. They still go off to infinity, like they can reach any value of y. It's just the values of x that you need to produce those are so enormous. So you're going to see that when you graph them. All right. So recall that an inverse, we can think about an inverse by reflecting in the line y equals x. We can just swap x's for y's. So here you'll notice these tables just swap all the things. And you can rearrange equations to find your inverses. Ours would be an example of equations that have been rearranged into logarithm form. All right. So we talked about this yesterday, actually, where I talked about 2 to the x looks something like this, and log base 2 of x would be its reflection in the line y equals x. So why is that? Well, you know, one of the ways that you'll often turn a function into its inverse is you just like swap the position of x and y. So if I have x equals 2 to the y, now, how would I isolate y in that equation? Someone tell me I could write it in logarithmic form. Yeah, we could log both sides and do a change of base, but and then use power law. Or you can just like write this in logarithmic form. So when 2, if we want 2 to output like x, we have to raise it to the y. So that is log base 2 of x equals y. Remember, the exponent itself is the output of a logarithm. So that would be the rearrangement. That's like just like the algebraic move it around. That's exactly what we have here. Let's go. So recall that we have these function transformations where a changes the amplitude of our like sine waves, but it's also just a vertical stretch or a reflection in the x-axis. K is a compression, so it's squeezing our functions this way, and it's also can reflect in the y-axis. D is our shift left and right, and C is our shift up and down. These are translations. They just change, they don't change the shape of the graph, they just change the position relative to the point 0, 0. So there is notes on that in the D2L if you're wondering, and I'm sure various Google searches and things could also be helpful if you find me to be unhelpful when you ask me questions. I don't know why you would. I try my best to answer your questions when you ask me questions, so ask away. Okay, so when you're sketching the logarithms, when you're creating your graphs, show me the vertical asymptote, the x equals line. The x equals some type of constant, say h or whatever. That's going to be a number. Okay. If there's, when there's always an x-intercept, so show me that. You just solve that by set f of x equal to 0 and solve for x. The y-intercept, there will only be a y-intercept if we have some kind of phase shift. Otherwise, the line x equals 0 is your asymptote. So in those cases, which are very common, we can just find one other point. Just find a second point using any value of x within the domain, or solve for some y value that you feel is convenient. There might be a particular point of interest, but if it's just an algebraic situation, fit one that's going to look pretty on your graph. Let's go. What are our transformations here? Well, I'll get started, but you tell me what they mean. What does that mean?
Being compressed by a factor of 2.
Sure. I like it. You could say vertically stretched by a factor 1/2. If you said vertically compressed by a factor 1/2, I wouldn't take away a mark, but I would be like, I ain't eaten got none. You know, like you got some double negative going on there. Some double compression. I don't know what that means. Okay, and then what else? What does that C value do? Yeah? Yeah. Vertical translation. Down 1. Good. So then let's find our stuff, and then we'll create a graph. So our intercepts. Let's let y equal 0. So that would mean 0 equals 1/2 log of 10 to the x minus 1. Okay, here we just Desmos swing that 1 over there. 1 equals 1/2 log 10 of x. Multiply both sides by 2. 2 is equal to log 10x. So this is saying if we rearrange this into exponent form, what will we have?
100.
Yeah, we have 10 raised to the power 2 equals x, which equals 100. Yeah, so now that gives us the point 100, 0. I mentioned these things are really flat horizontally, right, at a certain point. Wow, that one went all the way to 100. Okay, now if we try and solve for where x equals 0, we'll find we can't do that, right? Because here x is clearly greater than 0, because the argument of a logarithm is always greater than 0. It's asymptotic to 0, unless we shift it around with d. So what type of point do you want to look at next? We get to choose one more. That also gives us our asymptote, by the way. Yeah?
Can we look at when x is like, I think, 95?
We could. It's going to be gross.
It is. What should we do?
Well, what number would be nice to work with there? Log 10 to something. 10 is nice. 1 is nice. 100 we already got. You could look at 1,000, but I wouldn't recommend it. It's just going to be 1 higher. Then, oh wait, no, it's going to be half higher because we multiply that by a half. Okay, so you want to look at 10 or 1 for x? 1? Let's look at 1. Okay, so if we let x equal 1, then we have y equals 1/2 of log 10, 1 minus 1. What's the log of 1?
0.
Good. This is 0. So y here in this case is 1/2 multiplied by 0 minus 1. That's saying what power do I need to raise 10 to get 1? And anything to the 0 is 1. So that's why log 10 of 1 is 0. Log of 1 for any base is 0. Okay, so this gives us y equals minus 1. So we found that the point 1 minus 1 is on the function. Cool. So now we got these 2 points. We know that the vertical asymptote is x equals 0. So now we can go ahead and sketch it. So I'm going to get my asymptote pen, which is red and really thick. And I'm going to go down here. There's my asymptote. Isn't it beautiful, everyone? Aren't you so impressed with my graphical abilities? And then I'm going to get my function drawing bit, which is going to be a little thinner. I pick my slightly thinner pen. And I found that point 1 minus 1 is there, let's say, and then we're going to be asymptotic, so we're something like this. And we hockey stick like crazy. And you see where I crossed? Exactly at 100, everyone. So that's the point 100, 0, because I say so. And this is the point 1 minus 1 because, well, clearly it is. Okay, so there, that's a graph for all the marks. It's not beautiful, but it's fine. If you're looking at these in Desmos, liberally change the values of your scales so that you can see these clearly. And if you were like presenting your data to someone because your data was important, you would want to do the same and present it in a compelling way. Okay, y is equal to 4 times log base 2 of x plus 4. So I'll do this part, and you tell me what they mean. We stretched it vertically by factor 4. Okay, that's from a is equal to 4. And then we horizontally translate 4 to the left. Just like Mr. Wyville. He left before. Okay, all right, so now state the properties. Okay, this one, our asymptote is x must be greater than -4. So x equals -4 is our vertical asymptote. Cool. All right, this time we are going to get, because it's now going up and this way, we are going to get a y-intercept and an x-intercept. So we're going to find both of those. So for our y-intercept, just set x equal to 0. And then we have y equals 4 log base 2 of 4. 0 plus 4, it happens to be 4. 2 raised to the something gives us 4. Well, this thing here, what's the value of that? 2. Good. 2 to the 2 is 4. So that the exponent that we need to raise 2 to get 4 is 2. So this is y equals 4 multiplied by 2. So this is y equals 8. So that gives us the point 0.8, everybody. Now, to find the x-intercept, we set the whole thing equal to 0. So 0 equals 4 log base 2 of x plus 4. All right. Dividing both sides by 4 gives us 0 equals log base 2 of x plus 4. Okay. So, now what? How are we going to make progress here? Anyone at your table know?
Is it that 2 to the 0 is x plus 4?
Mm-hmm. Good. 2 to the 0 equals x plus 4. We used that skill from yesterday. Now what does that make x? -3. So 2 to the 0 is 1, and so that means 1 is equal to x plus 4. We subtract 4 from both sides to give us x equals -3. So that gives us the point -3, and now we have everything we need to create a nice sketch of this situation. So let's go. I get out my asymptote pen, which is red and kind of chunky. And I go over to -4. 1, 2, 3, 4. Oh, it's such a beautiful asymptote. And then I go less chunky here. And then we found 0.8, right? Y was 8. 1, 2, 3, 4, 5, 6, 7, 8, right? And then another one was -3, so 1, 2, 3. So there's our 2 points. All right, and so you can imagine that this thing is going to come up here, bullseye that point so beautifully, and at some point in here it starts to hockey stick like that, and it never stops increasing, but it really slows down. So it's going to look something like that. All right? I don't know exactly what it looks like. If I wanted to know what it looked like exactly, well, I would check a lot more points, or I would consult Desmos. So let's do exactly that. So we are interested in 4 log base 2 of x plus 4. How do I do 4 log base 2? How do I do base 2 in here? I'll do this later. I know what I'll do. Oh, wait. No, I can't. I can't bring myself to navigate to my email. Yeah?
You can put like a...
I think it's in here. Oops. Oh, this is fun, eh? The ultimate lesson, he says.
If you type like an underline, it'll run the subscript.
Oh, yeah? Oh, yeah, you're good. Thanks. It's 4 log base 2 of bracket x plus 4. There. Excellent. Thank you for saving me all of that embarrassment. So, it looks something like that, everybody, where it actually comes up a lot more gently than I thought and hockey sticks a little bit more gradually. But how would I train my intuition for that? I think if I visualize 2 to the x and translate that appropriately and look at its reflection in the line y equals x, like the corresponding exponential graph is somewhere down here, and it's asymptotic to -4 in the y down there. So yeah, that's how I can imagine it in future. Yeah. Cool, let's keep going. All right, so this one here, we got a lot more transformations to think about. So what are they? So vertical stretch by a factor of 2. What about this -1/3 here? Mm-hmm. By a factor of what? Sure. So that includes the idea reflect. How?
Quasi-stretch.
Yeah, but it also has, because it's negative, it also involves a reflection. So it reflects on the y-axis. So we multiply all the x values by 3 when we have that -3 there. So the c value is 2. So that's a vertical translation by 2 units. And then how about the horizontal translation? Excellent. We should definitely factor out that -1/3. So we should really rewrite this function as y is equal to 2 log base 3 of -1/3 factored out of x plus 3 plus 2. So there is our horizontal translation by 3 units. This one was up. This one is left, of course, left. In my brain, I'm visualizing left, but then it said right. Yeah, because that's positive, so it goes backwards. Okay, now, yeah?
Sorry, why is the horizontal stretch by -3, not -1/3? Like, compression?
Remember we divide by k?
Yeah.
Yeah.
Like,
So the k and the d are kind of counterintuitive. They always do the opposite of what you'd think. So when a and k are like analogous, right? In a we multiply the y values
yeah.
by a,
Yeah.
but for x, because x lies, or because x is doing the opposite of what you think it does,
Yeah.
when you have like a third, it stretches it this way,
Oh, okay.
because we divide the x values by k.
Yeah.
So dividing by a third is the same thing as multiplying by 3, because flip and multiply.
Yeah.
Okay. And if you recall, like all the good work you did on trigonometric functions, when you have something in there like, say, 10, then you have 10 times the amount of wibbles within the period,
Yeah.
right? Or so the period is 10 times shorter,
Yeah.
right? But if you had 1 on 10, then it's all stretched out. So it's matching what you saw in that unit.
Oh, okay.
Okay. So now let's state the properties. So if we rewrite, we just see it all that much more clearly. 2 log 3 times 1/3, but it's negative of x plus 3. So what is our vertical asymptote? X equals negative 3. Yeah, that's right. So what are our limitations on x?
Greater than negative
Hayden, thank you for being the bigger man. It's good, I appreciate it. X is greater than negative 3? Yeah? Really? Why?
It's less than because it's multiplied by negative.
We have to multiply by negative here. And so, this is a place where you could easily drop marks. Here is a way that you can solve it visually, is I visualize it, okay? I'm gonna have something here. I definitely know I have this asymptote there, and I know it's been reflected in the y-axis, so it's doing something like that, okay? So that's its reflection as I reflect it in the y-axis. So visually, I know that x has to be in that domain. X is less than minus 3. Algebraically, here's how I would find it. I would say, I know this thing here has to be greater than 0. So minus 1/3 times x plus 3 is certainly greater than 0. Okay, so now I'm going to divide both sides by minus 1/3. So that gives me x plus 3 is less than 0. You see what happened there? Why did I flip the direction of my alligator? I divided by negative. Yeah?
I'm kind of confused because the top is like x minus 1 and you got x plus 3. Can you go back to where you got the 3 from?
Oh, I factored this part out of this part.
Okay.
Yeah. So I divided both of them by negative 1/3, and negative 1 divided by negative 1/3 is positive 3.
Okay.
Yeah.
How do you know that what's in the brackets has to be greater than 0?
Because the argument of a logarithm is always greater than 0.
Right.
Yeah, that's part of our definition of a logarithm.
Okay.
So if we look at, look in Desmos, because I've got my trusty sidekick here who helps me with Desmos. When I say log of x there, I see like this is just like our parent function, our log base 10, and it's asymptotic. It starts there and goes positive. But also like exponent laws wise, if I have 10 raised to the power something, which is the output of the logarithm, okay, that something can be positive or negative. All right, that's no problem. But even if it's very, very negative, the output will be very small, but still non-zero. Like it was asymptotic to 0 from the positive direction when we looked at exponential functions. So now our inputs have to match that new domain. What used to be the range of an exponential function is now the domain of a logarithmic function. Because when you look at an inverse, domain becomes the range and range becomes the domain. So that's a long answer to your question. Satisfied now? For the most part? Okay, we'll continue. Okay, so when I divided by negative 1/3, my alligator flipped, and so then we found x is less than minus 3, and we don't want to drop these marks, and you don't want to get confused. So you'll be confused if your visualization doesn't match your algebra. So I would suggest doing both to reinforce the idea, and be sure that you have a very clear sketch with all the points making sense. Okay, so now we need some key points. Because we have a horizontal translation, we can find our x-intercept, but we will not find a y-intercept because we're going the wrong direction from y to find that y-intercept. So we get the freedom of choice. All right, let's first start with a y equals 0. So that's going to give us this point here. So if we have 0 equals, I kind of ran out of space. 0 equals 2 log base 3 of negative 1/3 bracket x plus 3 and the bracket plus 2. Okay, so we kick the 2 over and divide by 2. So we have minus 1 equals log base 3 of minus 1/3 times x plus 3. Okay, do you see how I got from here to here? Or am I skipping too many steps? I subtracted 2 and then divided by 2. Okay. So then, now I can rewrite this and yeah. Okay. 3, which is the base of this logarithm, raised to the power -1 is equal to -1/3 multiplied by x plus 3. Okay? Well, 3 to the -1 happens to be 1/3. And that's equal to -1/3 multiplied by something. What do I need to multiply -1/3 by to get positive 1/3? -1. So that makes x what? Yeah, x is -4 here. Another thing I can do here is divide both sides by -1/3, and then I will get -1 equals x plus 3, and -4 equals x. So that matches our visualization. If this is x equals -3, then we have here the point -4, 0. So that's convenient. And then what might you check next for another point? One. 2, like try y equals 2? Sure. Okay. I'm going to erase this little work I did here to find the direction that this thing goes, or the restrictions on x, so that I can work y equals 2. So what we're effectively doing is saying we're interested in this value y is equal to 2. What x value does that? Y equals 2. We get to choose, so Quinall made a choice. So we have 2 equals 2 log base 3 of -1/3 times, what did I do with this plus 2? No, I worked with that, yeah. Okay, I worked with it. It's good. I was just looking, I was like, wait a minute. But it matched our visualization so perfectly. How could I possibly have an error? Plus 2. Okay, so there, -2 from both sides gives you 0 equals 2 log 3 of -1/3 times x plus 3. Okay, and then we want to know, well, we can certainly divide by 2 both sides, so that goes away. So that is to say this is equal to 0. So now when I put this into exponential form, how do we solve for x? Yeah. So you have 3 to the power 0, which is 1. 3 to the 0 is equal to this stuff. -1/3 times x plus 3. So 1 is equal to -1/3 times x plus 3. Divide both sides by -1/3 gives you 1 divided by -1/3 gives you -3 equals x plus 3. And that makes x equal to -6. So there you have it. This point here is the point -6, 2. So now we've got this point and that point, and we can now create a beautiful sketch. So our asymptote was at -3. 1, 2, 3. We had, this is our intercept. And then when we were up at 2, we were over at 6, 1, 2, there. So now our function looks a lot like this. Whee! Comes up so close to its asymptote and starts to bend and move in that direction. It doesn't come up this fast, I don't think, at that point. That's a little bit high. I would predict something a little bit more like this. But we could calculate more points if we wanted it to be more accurate. Okay. And then label your points. So this is x equals -3, -4, 0, and -6, 2. Keep going. Let's go. Practice. So all the practice is textbook today. If you're like, but Mr. Jennings, I haven't carried that since February, then you go into the D2L and find it in the content in there. You can find the textbook there and practice these problems. You can also generate problems for yourself and graph them up and then check them in Desmos. If you'd like, I can generate some problems on the board and you can graph them. And then check your work at the end. But there's a quiz. So prioritize the quiz, and this is a skill we'll practice over the next couple days.